Given f of x equals parenthesis x minus 2 squared parenthesis x plus 1, it's sweet because they factored it for us. Find the sketch with all the intercepts and the proper end behavior. Okay, to start this, we're going to consider the degree of the polynomial. This is a degree 3 polynomial. How do I know this? Well, I could just multiply everything out and I would see the highest power on x is the third power. But since I have x to the first power inside each of these parentheses, I just look outside at the power. So the first factor, x minus 2, that's x to the first power minus 2, then it's raised to the second power. That means that when I expand it, it'll be x to the second power will be the highest. Then I multiply it by the second one, which has x to the first power inside and an exponent on the outside of invisible 1, which means that's x to the first power. Then when I multiply those two together, I would add the exponents on the highest power of x. 2 plus 1 is a third degree polynomial. Now, third degree means that it's odd. It's an odd degree polynomial. The lead coefficient, if I multiply that out, would be a 1 in front of x to the third power. And you can multiply it through if you want to see that. Do x minus 2 times x minus 2, FOIL that, and then distribute that across x plus 1. And you'll see there's a 1 multiplying x to the third power. So the lead coefficient is equal to 1, and 1 is a positive number. So odd degree with positive lead implies that the end behavior looks like this sketch. It goes down on the left and up to the right, and the way we describe this is y approaches negative infinity as x approaches negative infinity, and y approaches positive infinity as x approaches positive infinity. That's a description of the left and then the right side. So we know the end behavior of this graph is going to look like the cloud, what's in the cloud. We have to figure out what's happening in between. Let's do a chart, a table here listing the zeros, the multiplicity of each zero. Is it a crossing or a kiss? And what is the x-intercept? It's a crossing or a kiss. So I see 2 zeros, 2 roots, the numbers being subtracted in the factored form of the polynomial. The first one is x minus 2 in the parentheses. So 2 is our 0, our root. 2 is an even number. 2 it's a multiplicity 2 because the power on the outside of the parenthesis is 2, and that's an even number. We have an even multiplicity. That implies that the x-intercept will be a kiss. It's just going to touch and turn back. And then the x-intercept corresponding to the root, or the 0, 2, is 2, 0. Now, the next parenthesis in the given polynomial is x plus 1, which is x minus a negative 1. Right? Double negative makes a plus. So we're subtracting negative 1. That's the root here, or the 0 here. It's negative 1. Okay, now what is the multiplicity on this root? It is the power outside the parenthesis of the factor containing the root. It's the invisible 1. So the multiplicity is 1, which is an odd number, and that indicates we have a crossing. All right, odd multiplicity means the x-intercept is a crossing, and the x-intercept corresponding to the root negative 1 is negative 1, 0. So we got lots of information here. We're going to do a pre-sketch analysis of the information. So pre-sketch info. We're going to do just, let's see, the x-axis going across, and we'll put a y-axis in there. We don't really need the y-axis. Put the roots, the zeros. They happen at negative 1, and it happens at 2. Those are our roots. Okay. Now we're going to make a dot where the roots are, the x-intercepts. Okay, now list the factors in the factorization of the polynomial. X minus 2 squared, x plus 1 squared. We're going to figure out what the sign is on each of these roots in this region, and that's going to tell us what the sign of the total polynomial is in that region. So we're looking to the left of negative 1. Let's say x is equal to, negative 100. That's to the left of negative 1. Plug it into x minus 2 to the second power, we get a positive result. Plug in x equals negative 100 into x plus 1, we get a negative result when we simplify. So we have a positive factor times a negative factor equals the entire polynomial for values to the left of negative 1 Positive times negative is a negative for the factors x minus 2 times x plus 1. Negative, because a positive times a negative is a negative. That means the polynomial p of x is negative for values of x to the left of negative 1, which means it's below the x-axis. So you can actually sketch what happens to the left of the root negative 1. The graph is below the x-axis. Then we'll fill that in later. We're looking at the value, positive or negative, on each of the factors for x values between negative 1 and 1. See, it was kind of distracting to draw that y-axis. You don't really need to have that there. You're interested in values of x between negative 1 and 1, between successive roots. Okay, so choose some value between negative 1 and 2. Negative 1 and 2. Well, let's see. X equals 0 lives between negative 1 and 2. So let x equal 0, plug it into the first factor. It gives you 0 minus 2 squared. That's positive. Plug it into the second value. 0 plus 1 is positive. Multiply them together to get the sign on the polynomial. It's a positive times a positive is a positive. Finally, we take x values to the right of x equals 2. Let's say x equals 100. Plug it into each of the factors. Plug it into the first factor, x minus 2. You let x equal 100, you'll get a positive result. And the second factor, 100 plus 1, is a positive result. Multiply them together to get the sign on the entire polynomial p of x, the product of those two factors. Positive times a positive is a positive. Okay, so now we're going to see what happens to the graph in each of these regions. The polynomial p of x is p of x is determined by the negative, positive, and positive signs below the x-axis that I've written. So we have the graph below the x-axis for x values to the left of negative 1, above for values of x to the right. Now, I'm not telling you how far it goes up, but it's eventually going to turn around and come back. I just don't know what it's going to do up there, so I'm not going to continue it. To the left of 2, it's above the x-axis, and then to the right of 2, it's still above the x-axis because we get positive signs in each of those two regions. So this is the pre-sketch. It shows how the graph behaves on both sides of the roots, of the zeros. And we did that by doing a sine graph. This is a sine graph, doing an analysis of the function, positive or negative, above or below the x-axis. Okay, now let's find the y-intercept by evaluating the function f of 0. So use the given function for f of x. We get negative 2 to the second power times 1 equals 4. So the ordered pair 0, 4 is our y-intercept. Now we can put all of this information together to do the sketch. So putting everything together, we have the y-axis and the x-axis. We've got the roots at negative 1 and at 2. All right, we have the y-intercept at 0, 4, and we have the x-intercepts, negative 1, 2, and we know that we're below the x-axis on the left of negative 1, and then above between negative 1 and 2, and then continues above after 2. Use the pre-sketch end behavior information and a smooth, continuous property of a polynomial to sketch what this thing looks like. Okay, so our zero end behaviors. We know at the very end we're going to be going down, and on the very the left and on the right we're going up. But that's exactly what the pre-sketch information told us anyway. And there's our picture. It's a rough picture, but that's basically what our polynomial looks like.